Hello students, and welcome to today's lecture, which is going to be on alcohols and esters. And this lecture portion is really going to be more concerned with the reactions that we can have with alcohols, reactions to reduce them and to oxidize them and all sorts of different things. And also we're going to go over esterification as well, okay? And so what we're going to go ahead and do here for today is we're going to go ahead and do the 6 different reactions with alcohols. And then we're going to have a separate day just to distinguish the type of alcohols, and we actually have a brief little lab portion for that. But the first one is going to be a reaction with combustion. And those of you that have been in Mr. Bradley's class for a long time know that Mr. Bradley loves to light his table on fire. The irony of that is that it's one of the things that we are learning about here, in which case it's the burning and combusting of alcohol. And I'm always using some form of alcohol for this, whether it's ethanol, which gives a slightly bluish flame, or methanol, which gives a very clear flame. And the main idea with combustions of our alcohols is that we have a hydrocarbon compound. In this case, it has an extra oxygen. We combine it with oxygen, and then we use that to make carbon dioxide and H2O. Okay. And this will be just like with the alkanes. If we have complete combustion, it's going to make carbon dioxide and H2O. And if it doesn't have complete combustion, then we'll make carbon monoxide and H2O. The next reaction that we're going to go over is going to be substitution. And there's a couple of different ways that alcohols can undergo substitution. And one of the big key ways that we can go have alcohols undergo substitution is by adding a dry halide, okay? And a dry halide will be able to go ahead and replace the alcohol group, and we'll be able to make water from that reaction. We can also end up making the hydrogen halide in ceto. So for instance, in this particular case, if we add salt to sulfuric acid, we'll end up making a new salt and hydrochloric acid. And note that this is a case where we have to make sure that we're using concentrated stuff. The idea is that we can go ahead and get the chloride ion to go ahead and be the nucleophile, okay? So this would be an example of nucleophilic substitution. And when we have that acting as a nucleophile, it'll go ahead and exchange off with the oxygen, the alcohol group, and we'll be able to make our new halogen alkane based off of that. Okay, so this reaction is also done under reflux, and then we usually distill out our halogen alkane. And the reason that we can distill it out is that the halogen alkane is going to have a much lower boiling point than the alcohol group. And this is primarily due to the fact that the alcohol group has the OH group here, and therefore it's capable of doing some hydrogen bonding. And in general, when we have an alcohol group, it's able to do some sort of hydrogen bonding, and that makes it so that it's going to have a much higher boiling point than other kinds of organic compounds here. So typically what we'll do is we'll go ahead and add our hydrogen halide, and then we will go ahead and boil this under reflux, and when we boil it under reflux, we'll distill out any of the new hydrogen halide that way. The next reaction that we can use to go ahead and substitute out or do a substitution is to use this compound right here. Okay, and this compound, I completely forgot what it is called. So 1 second here, SOCl2. And this is called thionyl chloride. Okay, and thionyl chloride is going to be another way that we can go ahead and add this here. The idea with this one is that by using thionyl chloride, we're going to end up making hydrogen chloride gas and SO2 gas. Okay, so sulfur dioxide is also going to end up being a gas, which should leave us just with the liquid hydrocarbon right there left behind. The third way that we can go ahead and do a halogen substitution, if it is a chlorine, and these two are specific for chlorines, is that we can go ahead and use phosphorus chlorides. Okay, and these can be done at room temperature here. Okay, so this is an example of one that can be done at room temperature, and it does make some waste products of hydrogen chloride, and we also have this waste phosphochlorous molecule right here. If we were going to go ahead and try to add something other than chlorine, then in addition to the hydrogen halides that we have here, because the hydrogen halides will, in general always work, but in addition we can also use a phosphobromo type of structure where we have PBr3, or we could also use Pi3 if we're trying to add the iodine ion into our substitutive carbon chain. Okay. The next reaction part that we want to go over is the reaction with sodium metal. And we're going over the reaction with sodium metal because it creates a new kind of product that we want to go ahead and be aware of. It takes our ethanol plus regular sodium metal. Notice that this does not have any charge to it, and it's going to make ethoxide. We'll have a sodium ion that'll dissolve here, so we'll have sodium ethoxide, and then we're going to end up making some hydrogen gas. Okay, so in this hydrogen gas, if it is warm enough, it'll go ahead and light on fire. So that's partially why whenever we add sodium to water or other things, it ends up releasing hydrogen gas and lights on fire. So this is another type of reaction that you need to know for this section. The next one is what's known as esterification. And esterification is the process by which we go ahead and combine a carboxylic acid and an alcohol. And what's going to happen in this particular type of reaction is that we will have these two molecules are going to end up coming together. And as these two molecules come together, what we're going to notice is that this OH group that's on the carboxylic acid is going to end up splitting off. And then we're going to have the oxygen from this side go ahead and bond in there. Okay, and so our esters that we're going to have are always going to be from, or at least the ones that we're going to produce, we're always going to end up producing them from a carboxylic acid and an alcohol. And the water that we have made here is going to be made from the OH group of the carboxylic acid and the hydrogen from the alcohol. And then this part is really what's left of the alcohol that as it has combined up there. The next type of reaction is going to be a dehydration reaction. And remember, a dehydration is when we're trying to remove a water from a carbon compound. And for this type of reaction, what we have to do is we have to heat alcohols in the presence of a strong acid. And when we do that, we're going to go ahead and make some alkenes. And the temperature at which we have to do this is going to be dependent upon what type of alcohol it is. If it's a primary alcohol, we're going to have to do that at a relatively high temperature. We're going to have to do that at 170. A secondary alcohol has to be at least 100 degrees, and a tertiary is going to only be about 25 degrees. Just as a quick reminder that the types of alcohol, if the central carbon only has one carbon to it, that's our alcohol. If it has two carbons attached, that's our secondary alcohol, and tertiary alcohol is where the carbon has the carbon of the alcohol group has three different carbons attached to it. And this has primarily to do with the stabilization of the carbocation. The primary alcohol has less stabilization for that carbocation, therefore it is very much unlikely to go ahead and make this dehydration reaction happen. So for dehydration, just remember that the lower number of alcohols, the lower number of carbon groups around the alcohol, the more energy it's going to take to dehydrate it there. Okay. If we do not end up having enough energy to cause that break of bondage there, what'll end up happening is that instead we'll end up making an ether, and this is another way to go ahead and quote unquote dehydrate the alcohol, and this will just come from two alcohols that end up bonding together. So if you have enough energy, you're going to end up making an alcohol. If you do not do this in enough energy, then you're going to make an ether. And the last thing that we're going to go ahead and look for is for the oxidation of alcohols. And the oxidation of alcohols, remember that whenever we're going to show this with just that oxygen molecule being added here. And what you'll notice is that the main thing that we're always going to be concerned of for the oxidation of alcohols is that carbon that's right in the middle. Okay, that main carbon group here. So for primary alcohols, it's going to be this carbon. For secondary, it's this carbon. Tertiary, it's this one. And you can add both potassium permanganate, which is another substance that we've used to do oxidation, or you can also end up using potassium dichromate here. And the idea here is that when you add potassium dichromate here, what will happen is that the oxidation will happen on the alcohol, and if it's a primary alcohol, it'll go ahead and oxidize first to an aldehyde. And then if you continue to heat it under reflux, you can end up making a carboxylic acid. But what's really important here is that when you oxidize this compound right here, you're also going to be reducing the chromate ion as well. And when you reduce that chromate ion, what you'll end up seeing is that there will be a color change, and it'll change from orange to greenish hue right here. And when you do that oxidation, it'll let you know for sure, like, okay, I have had this oxidation happen and go through. For a secondary alcohol, what you'll notice is that instead of making an aldehyde, because that alcohol group is not on the end, it'll end up making a ketone, and then we'll have no further oxidation available to us there. For a tertiary alcohol, you're actually not going to be able to get any oxidation because there's going to be a lack of reactive CH bonds that'll help us with this. So there's not really a way for us to, attack that correctly with the oxidizer that we want to go ahead and add in there. And that's going to be the last bit for our section here on reactions of alcohols. One thing in particular that I want you guys to take note of is that when we do reduce this with either potassium dichromate or potassium permanganate, we'll make the aldehyde, and from there we can end up doing reactions on the aldehyde. The same goes for the ketone, and we'll learn more about these ketones later. The reason that we use potassium dichromate in this example is because it does give that nice color change here. Okay. And that's going to go ahead and close us out for today's lecture, and I hope you all have a wonderful day.